from Trinity College and the University of Cambridge. And her research uses computer simulations to understand and predict material properties with a particular focus on exploiting machine learning methods to extend the scope of atomistic simulation. She did her PhD in Michel Chariot's group at EPFL, and she's going to be talking to us about thermodynamic and transport properties of water and hydrogen machine learning potentials. I want to announce to everybody that this talk will be recorded, so anything you say will be part of our video and eventually posted on our website. Please, if you have any questions, you can put them in the chat field, and I will read them at the end. And otherwise, please enjoy the seminar, and I'm looking forward to hearing Dr. Cheng's talk.
Thanks, Paul, for the very kind introduction. And I also thank Jessica and Marius and Paul for inviting me. It's great to be here virtually. So I have been looking at material properties, particularly at high pressure, but I was always doing it from a theoretical perspective, which seems quite convenient during this troubled time. But anyhow, so I'll talk about computing thermodynamic and transport properties with some help from machine learning. It's a little bit of mouthful, but we'll break it down. So first of all, I want to thank my wonderful collaborators, Jörg Beller, Gary Brandenburg, Michele Charioti was my PhD advisor, Christoph Delago, Edgar, the wonderful Don Franco, Tomeo, as well as my very good friend Alex. Now, so just to put things into the big picture, so sometimes I ask myself, so from a theoretical perspective in computational physics, what is the biggest problem that we are trying to address? And actually, the answer was already given by one of the greatest physicists called Dirac almost a century ago. And he was like, the fundamental laws necessary for the mathematical treatment of the major part of the world are completely known. But the problem is that solving those equations are just way too complicated. So what is the solution? According to Dirac, we can develop a process method so that we can make those computations possible without too much cost. Now, and here I'm just going to show you a very standard picture of what are the theoretical treatment of materials and molecules, as well as the associated cost. Of course, at the very top, we have Schrodinger's equation that is virtually almost impossible to solve. And then we have the theoretical, we have the reference methods, quantum Monte Carlo, or coupled cluster, expanded to triplets. Those are of reference quality. And then the workhorse of the field is density functional theory with various levels of approximations. But typically, like these methods, what we call the first principle methods, are just too complicated for most of the applications. So usually, when we try to model larger systems at a longer time scale, empirical force fields, as well as like model potentials such as Leno-Jones or even hard spheres, are often used. Now, but that's not the only problem here. That the energy is expensive to compute when we think about first principles. Another problem, the major problem when we try to predict thermodynamic properties is actually the entropic part. It's the estimation of entropy. So here I'm showing the picture of Boltzmann's graph. And on top of Boltzmann's graph, there's the so-called the Boltzmann Equation. And it basically says the entropy of the system is the Boltzmann's constant multiplied by the log of accessible microstates. And a microstate is basically a specific realization of the system with specific coordinates and velocity of all the atoms. And what people don't always say is that this Boltzmann's equation is in fact wrong, or at least incomplete, because in reality, to compute the entropy, actually the sort of the relative entropy, we not just need to count for the number of states, but we have to weight them properly using Boltzmann's distribution. And this is just to show, like, to assess the thermodynamic free energy of the system, we not only need to compute the energy, but we need to sample the system in a thorough manner so we can achieve a decent estimation of the entropic contribution as well. Now, with that in mind, today we are going to talk about how does the machine learning potential help for us to sample the system, but still with relatively high accuracy. And then we'll talk about the system that we studied quite recently, hydrogen under high pressure. And I know that's also a focus of research in your research lab. And then I'll go a little bit deeper to look at to explain a little bit why does machine learning works at all. So basically, I'll talk about the locality argument. I'll talk about the local environments in liquid water, as well as the prediction of water phase diagram. Okay, so water is a rather strange system. It occurs in three phases in nature. It's dense at 4 degrees. Ice floats on water. It has many other unusual properties. And another sort of mysterious thing about ice phases is that it has two polymorphs, the hexagonal ice as well as the cubic ice. Now, the ice we see in nature, like in snowflakes, they are exclusively hexagonal ice. However, at the theoretical level, people haven't been able to distinguish the energy difference between cubic ice and hexagonal ice. Basically, if you use empirical potentials or density functional theory calculations, they will predict the two ice phases have degenerate enthalpy, which doesn't explain why all the ice phases in nature are hexagonal. Now, to go to the machine learning potential part. So, machine learning potential is supposed to be this wonderful combination of low cost as well as accuracy that is on par with the evolution method. And how it works from a purely black box point of view is that we have certain configurations, and then we label them using certain quantum mechanical methods. I wrote DFT, but it doesn't have to be. And then these configurations, along with forces, are then used to train a machine learning algorithm. It could be neural network, but it also could be something else. And then when the new structure comes in, and the neural network or other machine learning methods then can spit out speedy predictions. And I always feel deeply unsatisfied with such a black box point of view. So now I'm trying to provide alternative explanation why what is the underlying idea about machine learning potential from a more StackMac point of view. If I ask you to look at these two snapshots here, these two systems here, like, what do you see? And people might answer, like, okay, the snapshot on the left is an amorphous system. It's a liquid-like system. And the system on the right looks like a solid. And the reason why people would think the snapshot on the right looks like a solid, this is because if we zoom in and each environment, we can see repetitive atomic environment. If we sit on one atom and I look around in the system, like all local environments are FCC-like. Now, but in fact, not just the solids can have these repetitive environments. If we look very, very closely inside the liquid, we can still find environments that are very similar to each other. And this is, of course, very hard to see because it's a high-dimensional object. But we can use descriptors. We can use the representations, such as the slope representations, and amongst others, to describe the local environments, and we can compare them. In fact, even inside a liquid, we can find solid-like local environments, and I'll actually delve into this point a little bit later. So what does this mean? Like, what does this repetitive environment imply? This means if we do molecular dynamic simulations using first principles, it's actually very wasteful. The reason is that we see repetitive environments over and over again, and we use the locality argument, right? So if I'm sitting on an atom, the forces I'm experiencing and my energy is almost completely determined by my intermediate neighborhood. But however, like every time a atomic environment is encountered in the calculations, we have to recompute its energy and forces over and over again using first principle methods. So what machine learning potential is really like instead of recomputing the environment, I have a memory. Right? I have a memory that contains all the atomic environments along with the energy and forces associated with that environment in the memory. So next time I see a new environment, I just compare this new environment to the ones in my memory, and then I give a prediction. So to summarize, machine learning potential basically works by two steps. Step one, we collect a bunch of environments, and we know what their local energies are, and then when new environment comes in, we basically do an interpolation, right? So that's a very simplistic two-step process. Of course, I mean, of course, that all look too good to be true. Who doesn't want to have a model that has the first principle accuracy, but at the fraction of the cost? The reality is that training the potential itself is still quite tedious. I was quite lucky, but I also know people who spend years training a potential. So when people ask, is it worthwhile training a machine learning potential to study a particular problem? I mean, it depends, right? So a very simplistic view, just from a temporal point of view, if you just brute force it, if you can solve the problem using ab initio molecular dynamics, and think of how much time that takes. If it takes more time fitting a machine learning potential, then the correct approach is just to run an AIMD simulation instead of even attempting fitting the potential. So coming back to the liquid water, we compiled a training set, and the training set is computed based on a hybrid DFT level theory. This is graphic B0D3, and we use this because the potential, the functional has been thoroughly benchmarked. We used the Euler-Parinello neural network to train the potential, and we also put the training set on public domain. So the training set contains 1,500 also liquid water configurations with energy and forces as the label. And then 1,000 of these are from classical simulations by quenching. And then there are some that were selected from past integral molecular dynamic simulations. And this is the standard 45-degree line that all machine learning work has to show. And now we use the train potential to predict the density of 3 phases of water. So we have the liquid, we have the cubic ice, and then we have the hexagonal ice at 1 bar of pressure as a function of temperature. So the stars. So the stars are experimental measurements, and the dashed line. So if we look at this red dashed line here, this is the density of classical water. Right? Classical meaning that we don't consider nuclear quantum effect and we treat hydrogen as a classical particle. And then the solid line here indicates the density for H2O in accounting for nuclear quantum effects. So counterintuitively, nuclear quantum effects actually makes water a little bit denser. The same goes for the ice phases. So we have the classical ice phases. The cubic ice and hexagonal ice has almost the same density. Nuclear quantum effects makes it a little bit denser. So in general, we are always seeing like 2 to 3% of experimental error, and this is on par with the best water model available out there. And also we have a very good prediction of the radial distribution functions compared with experiments. So this is oxygen, and for oxygen, hydrogen, or hydrogen, you can see turning on the nuclear quantum effects has a major effect. And it's only after turning on the nuclear quantum effects that we reach a very good agreement with experiments. And then I want to talk about a little bit the thermodynamic properties, right? Namely the chemical potential that gives free energy. So our standard workflow is the thermodynamic integration. So the idea is that we start from a harmonic reference system because the free energy of a harmonic system is analytic. And then we do a step of thermodynamic integration to evaluate the difference between our actual system and our reference system. And then we do another step to include nuclear quantum effects. And now I'm going to show you something that may make you feel a little bit uncomfortable. So I did the thermodynamic integration using 2/5 of neural networks. And I'm here showing you the chemical potential difference between cubic ice and hexagonal ice. And here there's a big discrepancy. And of course, I mean, in the absolute terms, the difference is small, on the order of 1 MeV. But still, one can reach not just quantitatively, but qualitatively different predictions because of the residue error in the neural network, because of various reasons. So, first of all, the neural network that we are using doesn't have the long-range interaction. And then other than that, one can still have some residue error in the fitting. And there's another more subtle source of error, which is the representations that we use for atomistic systems were shown to be not complete. It is one of the recent studies. So anyhow, but even with the imperfect neural network, we still want to do some predictions. And so how do we do that? So the idea is that we have two potential energy surfaces, right? One is described by the ground truth, which is DFT in this case, and the other is the machine learning potential. The two potential energy surfaces are very, very similar, but they are ever so slightly different. So we want to promote our neural network results, machine learning potential results to the DFT level, and we have to do this correction not just at one point, but for different configurations. So to put this down mathematically, like we write out the Gibbs free energy for the system described by the DFT, which is basically the log of the partition function of the system, and we do the same for the machine learning potential. And then one can easily show that the difference between the free energies at these two levels of theory can be written in the form of the weighted the log of weighted exponential of the difference in the potential energy. So this is the standard free energy perturbation method. Now, typically, people don't do much free energy perturbation when performing free energy calculations because the convergence here is usually pretty poor. But in this case, the free energy perturbation is actually the perfect solution because the two potential energy surfaces are exceedingly similar. So the difference is very small. And in the end, I was able to converge the results. I was able to converge the correction term. So here I also divide by the number of atoms to look at the correction on the chemical potential. I'm able to compute this correction term, which then allow us to bring our machine learning potential prediction to the actual DFT level. So this is the magnitude of corrections for various phases. They are, in general, very small, on the order of MeV. So it's probably only needed if you are as pedantic as I am. So after adding this correction term, then we actually arrive at statistically indistinguishable results for this problem I was showing before, the chemical potential difference between cubic size and hexagonals. So to summarize the workflow, so the first part remains the same. We perform free energy calculations for the classical system as well as for the quantum mechanical system with the actual physical mass of hydrogen atoms. And then but in the end, we always add this correction term to bring the machine learning results to the actual DFT level. And then I just want to expand a little bit on nuclear quantum effects. And I also know, in your lab, there's also the difference of the difference between results coming from deuterium and hydrogen can be significantly different. The nuclear quantum effects affects many physical properties, such as the particle momentum distribution, heat capacity, hydrogen bond and diffusivity, and so on. And one of them is the isotope fractionation, which basically means in different phases of matter, we have different equilibrium concentrations of the isotope. And this is actually a very good benchmark to assess the accuracy of the potential energy surface, because it's very sensitive to the assumed potential energy surface. So and then also for the thermodynamic integration step from the classical to the quantum mechanical nuclei, one can also use so in the previous step, we typically use the past integral molecular dynamics formalism to evaluate nuclear quantum effects. So in this picture, each particle is represented as a ring polymer that is connected by a harmonic spring. So this formalism also allows us to perform thermodynamic integration from the classical to the quantum mechanical system. So roughly speaking, the biggest difference when we do this, the difference between the free energy between the quantum mechanical and classical system is basically an integration of the quantum mechanical kinetic energy, and if all particles were to behave classically, so for example, if you look at this water molecule here, if it were classical, then in each vibrational mode, we should observe the energy of half kBt because of the classical equipartition theorem. But this is most definitely not the case because of the nuclear quantum effects, and particularly coming from the 0-point energy. And here I'm just showing you the extent of quantum kinetic energy in different modes, in different vibrational modes in the water molecule. and then we do an integration of this kinetic energy from the physical mass of the system for hydrogen is 1 to the infinite mass, which is the classical mass. And this value then gives us the difference in the free energy between the quantum mechanical and the classical system. Okay, so without further ado, I'm going to show the results from water. So the standard workflow goes like we compute the difference between the chemical potential between cubic ice and hexagonal ice at the neural network level. We add the correction to bring it to the DFT level, and then we consider nuclear quantum effects. The interesting thing here is that nuclear quantum effects significantly stabilize hexagonal ice. So without nuclear quantum effects, the snowflakes that we see in nature may no longer adopt this six-fold symmetry. And as another example, we computed the chemical potential difference between hexagonal ice and liquid water. So basically, we compute at the neural network level, and then we add correction to bring it to the DFT accuracy, and then we add nuclear quantum effects. We consider separately D2O and H2O, and then we can also compare with experimental results. So you see, the agreement with experiment, the agreement between H2O, so this is the DFT H2O, and experiment is extraordinary. And not just that, we also correctly capture the difference between the melting point of H2O and D2, which is about 4 degrees experimentally. So that's all for the machine learning potential for water. And that actually, water actually sounds awesome thing, but hydrogen is a matter that is higher up in the sky. So high pressure hydrogen is interesting because it constitutes the major part of the center of the Jupiter. Usually I have a slide to explain my very rudimentary understanding of how people perform experiments on high pressure hydrogen. But for the purpose of this talk, I have deleted that slide. So experimentally, also theoretically, there has been a huge discrepancy on where exactly is the liquid-liquid hydrogen transition point. And like of course, I'm aware there are many very nice experimental results coming from your lab. And between different experiments and between different simulations, there's a considerable discrepancy of up to 100 gigapascal. And the traditional way of looking at this from DFT simulations or quantum Monte Carlo is to, of course, in that case, we are restricted to a relatively small system. And then we look at the pressure and density curve. And so here I quoted the previous results from Lorenzen. And then this discontinuity, this liquid-liquid transition, if it's a first order transition, it manifests itself in a relatively small jump in this pressure and density curve. This jump is tiny. So what machine learning potential can do is to give us a much larger system size and also give us much longer simulation time. This is mostly due to the much more favorable scaling compared with DFT methods or quantum Monte Carlo. So with that, we were able to scan the whole phase diagram of hydrogen. So here I'm plotting out the order parameter here is defined as the fraction of bonded hydrogen over a wide range of temperature and pressure. And then we have the melting line here. So this black line is the melting line. And above the melting line at low pressure, low temperature, like the system is mostly molecular. But as the pressure goes up and temperature goes up, the system gradually becomes atomic, and we didn't observe any sudden jump. And here I also overlaid many points, and some of it are from the experiments from your lab. Here are many lines here, but I'll walk you through it. And so the first thing to see is that there are this orange line and the purple line. And what are they? So we were looking at the density as well as the heat capacity at constant pressure conditions. And we saw this anonymous behavior. So if we look at the density curve here, right? So the liquid hydrogen exhibits a density maxima at 2,300 Kelvin, as well as you can see the peak, the maxima of the heat capacity. So we trace the location of we trace the loci of these maxima, and we plot them together with the order parameters. So you can see the two lines here are sort of trending towards this high pressure, this high pressure, low temperature region, and it seems to there's some trend for them to converge. We wish to understand it a little bit more, so we use this regular solution model that one can also find in certain textbooks. So in the regular solution model, so if we have a solution that is made with two components, A and B, then the free energy of this composite system can be written in the form that has three major components. One is the chemical potential. So X is the fraction of component B. So we have the chemical potential contribution, and then we have this entropic contribution of mixing, and typically there's an enthalpic penalty associated with the interface. So that's the third contribution. And all these terms like going together, that gave us a picture like this. So when the temperature is higher than the critical temperature of the system, the two liquids should mix completely. It will be a perfect mixing. So when the critical temperature when the temperature is lower than the critical temperature, then the two liquids will then phase separate. Now the name of the game is that we want to compute this free energy curve as a function of molecular or atomic fraction. And to do that, we used metadynamic simulations, and we compute the free energy curves across a wide range of temperatures. So these individual curves are actually at a different temperature. Across a wide range of temperature and pressure conditions. And then we fit these free energy curves to the regular solution model. And we have two fitting parameters. One is the chemical potential difference between the two phases, and the other one is the enthalpic penalty for the mixing. Now, so these are the fitted values of this delta G, the chemical potential difference, and omega is the mixing enthalpy. So we can see like and then we can fit relatively simple and empirical models to these delta G and omega values, and all works pretty well. And once we have this regular solution model working, we can then infer what is the critical temperature and what's the temperature under which the two systems will start to phase separate. So going back to this curve, so we have this, so the dotted green line here is the temperature under which the two systems will start to phase separate, and this dashed line here is the temperature under which the two liquids are equally stable. And the intersection of these two lines is just the critical point of our system. And so in our prediction, the critical point happens to lie on top of the melting line. So which means above the melting line, the liquid hydrogen system behaves as a supercritical fluid. So we also did some predictions of the solid phases. And in fact, our machine learning potential is also able to capture correctly the ground state. I mean, with respect to the underlying theory, what are the ground states? What are the solid hydrogen structures at various pressure? We also get the melting line in a reasonable shape. So that's all for hydrogen. And I want to explain a little bit more why the machine learning potential worked at all, sort of to rationalize it a bit. So remember this two-step, this very simplistic two-step picture. So first step is that we collect the atomic environment, and then we perform the interpolation. And then notice that during the first step, I'm relying on the fact that during these two steps, I'm relying on the fact that the total energy of our system can be expressed as the individual contributions from individual atomic environments. But is it true? Is this statement really just a mathematical device, or does it have any physical meaning? So to that aim, I was looking at this atomic energy. I was comparing the atomic energies from two fits of the neural network potential, and you see they're not correlated at all. So this is for the water system. And I was thinking maybe this is just because, a water molecule has two hydrogen and one oxygen, and depending how the energy is partitioned, you have this difference between different fits of neural nets. So instead, I compare the molecular energy, the energy of the whole water molecule compared across these two fits of neural nets. There's still a very poor correlation, which really tells us this atomic energy is more a mathematical device rather than it doesn't have a very solid physical meaning, which is a little bit problematic because because for a while I was very interested in computing transport properties, particularly heat transportation, which measures how well a matter conducts heat. So the orthodox way of computing the heat conductivity is to go from the Bingqing equation, which tells us the heat conductivity can be evaluated by integrating the autocorrelation function of heat flux. This equation is actually not practical if we are taking it seriously, because the Bingqing equation calls for integrating to infinite time. But because of the accumulation of the noise, if you integrate to infinite time, it will for sure diverge. So in practice, people do a cutoff in time, which may or may not be ideal if the autocorrelation function has a long decaying tail. But another problem is that the heat flux is then returned in this form, which has two components. One is the local energy, the atomic energy, times the velocity of each atom. But I have just shown that the atomic energy, at least in the neural network, is not a really physical property. And then the second term in the heat flux is also problematic. So it calls for this pairwise forces between two atoms, which is also rather hard to obtain because the neural network potential has many body potential. It's very hard to single out the pairwise interaction. Luckily, we found another formulation that helped us to circumvent the problem completely. So instead of going from Bingqing, what we did is that we were taking we were looking at the density field inside the bulk material, which just means that if we imagine if you take a Gaussian on each atom, and then you form a phase field representation of your matter, so you arrive at the density field. And in reality, one doesn't even need to put a Gaussian. You can put a delta function, which is indeed what we used. And if we do a Fourier expansion of the density field in space, which, by the way, is always a good idea. I was told during my undergrad, if I don't know how to do a problem, just take a Fourier expansion. If you take a Fourier expansion of the density field in space, and then we can show this rho at each k is the wave vector, and if we take the autocorrelation function of this rho k and t, this follows the hydrodynamic equation. And when we look at the functional form of this autocorrelation function, it has two parts. One is this decaying mode, so it's exponential minus something. So this is the sort of exponential decay mode. It's the heat mode that is determined by the heat conductivity. And then there's the second decaying mode that is related to the sun propagation. We did this. So with that, this basically means one can compute the heat conductivity just from a trajectory of molecular dynamic simulations and do this whole analysis as a post-processing step. So I just took a trajectory that I obtained earlier from the simulations of high pressure hydrogen using the machine learning potential. So this is the aforementioned autocorrelation function, and then we fit the autocorrelation function to the hydrodynamics equation, and this is the estimate of the heat conductivity of high pressure hydrogen. And then I'll just spend the last 5 minutes also to talk a little bit about the local environments in liquid water. Because previously I painted a rather sort of discouraging picture about this non-locality of the machine learning potential, but all is not lost. So when I look at my water machine learning potential, I had this question since long time. So my water potential is actually only trained on liquid. However, it describes the cubic ice and hexagonal ice phases very well. Why is that? They are not in the training set. And what about all the other ice phases? So I took a data set from a comprehensive survey of ice phases, and I used so in the original work they used a sketch map representation to select promising candidate ice structures from a very comprehensive set of more than 10,000 structures, and then we took these candidate structures, and now I'm just plotting them using a different dimensionality reduction algorithm. And now if I look at these 50-something ice structures and I compare them with the liquid water configurations in my training set, I project them down on this low dimensional representation so we can visualize it. We can see the ice and liquid are very different, which come with no surprise. However, the interesting thing is that if we instead not compare the whole structure, but focusing on compare the local environments, we can see the water explores the local environment in water almost completely covers the environments, the local environments that I found in ice phases. So this has implications. So I used the same neural network that is only trained on liquid water to predict various properties of ice phases, such as density and density and lattice energy, and I compare them with various DFT calculations. So the agreement is quite good. The agreement between the machine learning potential prediction and difference is on par with DFT is on par with the spread between different DFT functionals. We also computed the vibrational density of states at the machine learning potential level, as well as using ab-initio calculations. And for all the ice phases, we have very good agreement. This is perhaps a little bit hard to see, but we can zoom in to a few phases. And that also gave us hope that we can use the exact same machine learning potential to compute the ice phase diagram. And we did just that to, again, to bring you attention to the workflow. We start from a reference. We do thermodynamic integration to the machine learning potential level. We add correction to bring it to DFT, and we also account for nuclear quantum effects. And this is the result. This is the final result that we got. We have the experimental phase diagram. We have the phase diagram predicted by the machine learning potential, and then we correct this result to different levels of density functional theory. Graph B0D3, BB0D3, B3 lift is probably a more popular one, as well as adding correction. So as well as adding nuclear quantum effects. So you see the correction to the DFT level already improves the agreement with experiments. And overall, we have a fairly good agreement with experiments. This is the phase diagram that we are able to predict here. The quality is higher than the empirical water models that we had before. And to dig in a little bit more, the nuclear quantum effects again plays a major role. So on the right-hand side, there's a heat map of how nuclear quantum effects affect different phases of ice. And on the left, I'm showing you the phase boundaries of classical water, H2O, and D2O. At low pressure, surprisingly, nuclear quantum effects doesn't have a major effect, but at high pressure, when we are approaching 10,000 bar, then the difference are quite significant. And with that, I was also just reading this paper from your lab about high pressure water, the super ionic water and ice, and I really like this work. And in the future, we are thinking about using the same framework, machine learning potential plus DFT, or maybe other quantum mechanical methods, as well as nuclear quantum effects. We are planning to probe this region of the phase diagram as well. And I thank you for your attention.
Thank you very much. It was a very nice talk. I invite everybody to unmute yourselves so you can give Dr. Cheng a nice big applause.
So thank you so much. I think there will be many good applications coming from this new method. So it's very exciting. So thank you for sharing all these things. But with any new methods and anything you do at the beginning, you will ruffle some feathers, you will new things we couldn't do before. And there's also the chance that maybe something you do will not quite work the first time, and you will surprise everyone. So we talked about your paper on hydrogen in our group meeting. And you basically showed when you have machine learning and you go to much larger systems, the critical point goes down in high temperature. So we, in our group, we could not determine whether you just get this critical point to go down because you used a much larger system, or there was a problem with your neural network. So we wasn't sure, because how can we verify whether it's actually the larger system and not a problem with the network?
Mm-hmm. So there will always be this problem with machine learning potential, right? I mean, it is different. It's not the ground truth. And the best we can do is to verify it as much as we can for small systems.
This is Sebastian Hamel. I think this is wonderful work. I think you've so one thing, two comments. One is relatively minor, but on the thermal conductivity, that's for the ions, right? I mean, there's you know, once the electrons start conducting, that's going to be a very different calculation. But that's a minor thing. The more important question here is, I think one thing that you showed is that the machine learning model is not really modeling what the forces between each ions are. It's giving you a global, you know, idea of what that energy is for that particular configuration. So it's more like it remembers something right, from the training set. And as such, how do you see it going forward in order to basically make it learn more something that would be cast as an atom-centered energy, so that we can turn this into real potentials?
Well, as it is, it's already atom-centered. So we have we have each environment, and this environment is described by a list of descriptors. And we need the list of descriptors because it removes the rotational and permutational and translational variance. And then this list of descriptors that describes the local environment goes into the neural network and give you this local energy.
Right, but on a different slide, you were showing that you got different local energies for different neural networks, which means you don't really have one specific decomposition, right?
Right, but in the end of the day, like in the end of the day, like I think the idea of local energy, even at the physical level, is flawed because the energy of an atom comes from the interaction with other atoms, right?
Yes,
which is intrinsically non-local, right?
Yeah. And just the notion of where the atom is in a molecule is an issue, right? But it's sort of central to this idea of turning this into potentials, right? Believing that something can be made atom-centered is basically the first step in thinking of the system as effective interactions between atoms. So I just want to put it out there. I mean, that's sort of something I've been worried about with this approach for a while. But
Hi.
There are a bunch of questions.
Hi, this is Su-Xin Hu from University of Rochester. Thank you for this very interesting talk. Again, like Burkhard Minitzer, your recent Nature paper on the hydrogen liquid transition work really caught our eyes. And one of the reasons in your paper, you mentioned that for the past 2 decades, people doing the ab initio molecular dynamics might miss this important thing of the forced order transition because of the system size. So inspired by your work, our group in Rochester really put this into a test. So we put 2,048 atoms in a ab initio molecular simulation. And we do still see a sharp transition. So my question is that possible your machine learning, you training in the molecular side and atomic fluid side, they might not know each other when they cross the boundary. Is that possible?
So, to have a historical account, we actually have many generations of the machine learning potential. And how do we train it? In the end, we took a self-consistent, sort of iterative approach. How do we do it? Is that we train a machine learning potential, and then we build metadynamics to sample all the possible molecular fractions And then we recompute these configurations using DFT. And then we look at the difference between the predictions between machine learning potential and DFT. And we do this repeatedly until the two results absolutely converge. And another thing is that, so we also took the data set that is from Redmond and Auckland. So they have some DFT results for 500 atom, more or less, system. And then we look at them, and our machine learning potential can give very accurate predictions of the energy and forces of their larger configurations. And also, I'm quite interested in your evolution molecular dynamics simulations, and I'll be very curious to see like where.
Yeah, definitely. We'll let you know that we have like more than 2,000 atoms in this simulation. So yeah, thank you.
There are a bunch of questions in the chat that I wanted to get to. So there is a question from Burkhard Militzer on would there be a difference in pressure between DFT and machine learning?
Sorry, the difference.
That was a minor thing that was about slide 6. So maybe you go back to this, you write it as a Gibbs free energy difference. So normally I've seen these formulas for the Helmholtz free energy when there's no pressure term, but I mean, this guy was wondering if that makes any important difference.
It actually makes no difference because when you do the free energy perturbation, right? So this PV term cancels out.
It's not obvious to me, I have to say, because you have the pressure that you get for a configuration. I think is different in machine learning and in DFT, so therefore it would be weighted differently. I don't see it why it cancels out. That's also just a minor thing.
Right, but the pressure here should be the external pressure. It's not the instantaneous pressure of your system.
Okay, that makes sense. Okay, thank you. Yeah.
There's a question from Amit Samanta that if the energy difference between DFT and machine learning is small, then convergence to the free energy can be tricky. Any thoughts?
So my understanding is like if the difference is small, the convergence is fast.
I think he was worried that if the difference between the energies are small. Maybe Amit, you can clarify.
Yes. So what I wanted to actually ask, and I didn't state it clearly, I'm sorry, is if the difference is small, that means the contribution to the total to the Gibbs free energy difference would essentially come from regions where the discrepancy is evident, and that is where U DFT is not equal to UML. And are you sure you have enough samples in those regions that the free energy difference actually converges very nicely?
Yes. So the difference here is very small, and we are typically able to converge to this level of statistical uncertainty using just like hundreds of snapshots.
I see. Okay, thank you. I actually have another question, and maybe you can actually tell us a little bit more. So if you write the total energy is equal to sum of individual atomic energies, where atomic energy is not very well defined, but the underlying assumption is that each of these atomic energies are calculated or somehow depends on the local environment, then how come two different potentials that are calculating the same atomic energies based on the same local environment with similar, like 6 angstrom cutoff radius, that is what you showed in one of your slides, not be correlated?
Right. So I think there are a few reasons there. So, for example, for water, right? So if you have a water molecule, even how do you partition? You have let's say we have a OH bond, and how do we partition the energy coming from this OH bond to O and H? That already makes a major difference, right? And then beyond that, there's also this like long range interaction that we do not consider, which also contribute to the difference.
So, well, you are not considering long range effects, so that means the atomic energies are based on only the local environment within the cutoff radius.
Mm-hmm.
So based on your formulation, then how come two different neural networks have atomic energies that do not show any correlation? Because you have not included long-range correlations, as you just said.
Right. So the neural network tries to give the best fit to the total energy, right? But it has intrinsic limits because it doesn't see very far, and also the descriptor may not be complete. And then it tries its best to do this like impossible task. And then if you think of the loss function, this loss function has sort of a complicated landscape. And one neural network ends in one local minima, and the other neural network ends in another local minima, and there are different solutions. Although, if in terms of the loss function, in terms of the total training error, they are both very low.
Okay, thank you.
So Xuxing had a question about using machine learning for phase transitions and how confident one can be in such a method.
So for phase transition, so for the water case, we correct everything back to the DFT level. So the machine learning potential is really only used as a surrogate model. It doesn't affect the final result. For liquid hydrogen, we couldn't do that because it was not a. I think one can if one do an umbrella sample. Maybe that's possible, but it's less straightforward to do this correction. So that's also the reason why, in the case of high pressure hydrogen, we fit this sort of regular solution model to the machine learning prediction, which then gave us a sense of what are the sort of the error, what are the confidence, what kind of confidence do we have? So, for example, for the case of hydrogen, the difference between these two lines, the phase separation line and the coexistence line, depends how far they are. That gave us a sense of what kind of error can we tolerate.
And Zhao Wu asks, how big is the Gibbs free energy difference between conventional TDI results of ab initio MD and in a small system and machine learning potential in a large system corrected to DFT level?
I personally have not used thermodynamic integration with DFT. I think even for small system size, it can get really tricky.
And how do you correct to DFT level? Also, so how many key points? Just a gamma point when you calculate the internal energy to the DFT level for a large system. How do you correct that?
So we did this correction for the water system, and we did test. So we were using CV2K, so only gamma point available, but the system size was very large. I think we probably have like 96 molecules or something in the system, and it's amorphous. So for the liquid, it's amorphous.
So gamma point is enough, right? For the DFT level, correct?
It's system dependent. For water, also even proton disordered ice phases, it's disordered enough that for that particular for the structures that we consider, like something like 96 molecules, I recall, and gamma point in CV2K seem to be sufficient.
Oh, thank you.
But I wouldn't generalize this to other systems.
Thanks.
Since we're on the
There's a
slide,
question.
let me make another comment. The first order phase transition in liquid-liquid hydrogen has a long tradition. But the first person who actually showed it with ab initio simulations convincingly was Miguel Morales. So and the Lorentz work that you showed actually came after that. So since you're giving a talk at Lawrence Livermore National Lab and Miguel Morales is a good and very famous employee, I feel the need to point that out.
Okay.
So, but it doesn't matter. There are too many papers to cite, so don't worry about it.
Yeah, I have this very bad habit of actually not reading enough. Sometimes we basically just go for it, and then when we write up, we try to do a proper literature review.
Sure, no problem. No problem whatsoever.
The problem I find is that if I do a proper literature review beforehand, then I basically lose all the confidence in doing anything. I feel like everything has been done.
There is a question from Domingos. Could you explain again how you incorporate DFT corrections into the model?
The DFT, sorry?
Corrections into the model.
The DFT corrections to the model. So that's for liquid water. So it's simple. It's relatively simple. So we take a configuration. We first run MD or PIMD simulation using the machine learning potential, and then we generate many samples, and then we and it's better if they are decorrelated, and then we take these samples into DFT calculation, and then we can compute this delta U term, the difference between the DFT and machine learning potential. And then we do this exponential average to compute the correction term.
Okay. And one last question from Yubo Yang. At the same system size, given the same amount of simulation time, do DFT and machine learning get the same order parameter for the dissociation transition of hydrogen?
So our predictions of the critical point are mostly based on metadynamics simulations, and that require quite a bit of simulation time, I think. I mean, I was definitely not in the position of, I definitely didn't have the computational resources to run ab initio molecular dynamics for that system size and simulation time. So.
Hello. So yeah, I asked the question. So I actually go by Paul. I'm a new postdoc at Livermore working with Miguel Morales. And mostly I was interested in the first question that Burkhard asked, that is, how can we know for sure that the smooth transition you're seeing is because of the system size rather than the machine learning, some artifact in the machine learning model? So what I'm thinking, there are two worries. One is that if you go across this, like I've seen that you've done like excellent work studying the solid and the liquid in their own states, but I'm worried that as you cross the transition between these two states, in some transition states, the machine learning has some weird artifact that's not capturing the correct ground truth. So that's the first worry. And the second worry is that the machine learning has a fixed complexity, and you're studying a huge range in the phase diagram. Is it possible that you're spreading out its capability to capture the ground state energy surface over this wide range, that you're not really getting the details of this transition well? Is it possible that you shrink your window of study into a tiny bit across the liquid transition, and you instead see a first order transition?
So to answer to your first question, I think one can never rule out the possibility that there's an artifact in machine learning potential. It's like proving like there's no flying Chinese teapot around Jupiter, right? So what one can do is basically to rule out the obvious and testifiable possibilities, right? So regarding your second point, is it because we try to aim for too much? That we have tried. We have fitted machine learning potential just for the transition region, but the picture hasn't changed, right? And we did and we did some other things as well. So for example, at some point we were thinking maybe our machine learning potential has this artifact because some training sets, the system size was small because they were taken from DFT calculations. And then we fitted neural networks that use larger system size, like 500 something atoms, right? And then we took the configurations from Radma and Romain Auckland, and then we trained on their calculation. We trained on their configurations and see, because it's like the point that you hinted, right? Because the transition region is rather delicate. Is it possible like we don't have that transition region in our training set, right? So we took their configurations and we trained on them as well, and it didn't make any difference.
I see. Yeah, thanks.
So all I can say is I think we ruled out the obvious possibility, but there's never any guarantee that there's no artifact there.
I see. Thank you.
Hi, this is Marius. Yeah, I was just going to make a comment for the people interested. We're going to have an informal discussion on next Wednesday. So if you're interested to join that informal discussion, I see that there's a lot of interest in going back and forth and grilling Bingqing about her great results. So let me know if you want to join next Wednesday for an informal discussion.
So your email is Milo1?
Yes.
So Milo1 at llnl.org.
Correct. Yes.
Yeah. Okay. And I want to thank Dr. Cheng again for giving us this seminar. And yes, it looks like there's lots of room for discussion. I hope that leads to fruitful things down the road. Great for all of you guys. And I wish everybody a good rest of your Thursday. And please unmute yourself so we can give the next speaker again. Thank you.
Thank you.
Thank you.
Beautiful work.